can't decide if I want to say good morning or good afternoon, so I'll go with good morning. And it's great to see all of you here today. I am Carl Lejwe, the provost here at Stony Brook. One of the things that Monica Bagayo and I, our vice provost for faculty development, had really thought a lot about was how do we take the provost lecture series and align it with showcasing the best faculty that we have here at the university and providing an opportunity to bring in truly special external presenters. And it turns out today we have an opportunity to sort of do both of those. And we are just really pleased to have a talk today with Dr. Barish. He is obviously an incredibly brilliant individual, but what I have come to learn is also how intellectually generous he is, his humility and how he approaches the work he's done, his commitment to students. It is not every day that you meet someone who has accomplished as much as he has, and yet at the same time, what you're thinking about is how much you admire his humanity and who he is as a person. And so I think we are, and Chen Qi, who did so much to bring him here, we are just really thrilled to have him here at the university and then to have an opportunity to hear about his truly transformative work. Barry came here to be a part of the Department of Physics and Astronomy. This is one of our truly signature departments. It's a large department. It's a complex department. It has a variety of different facets and expertise, and includes a connection with the Xian Yang Institute for Theoretical Physics, the Simon Center for Geometry and Physics, the Laufer Center for Physical and Quantitative Biology. It also has a great partnership with Brookhaven National Lab. And it's not surprising that the department consistently ranks as one of the best physics and astronomy departments in the country and in the world. Part of that is because of the great faculty. Faculty awards include Nobel Laureate, Breakthrough Prize, Fellow of the American Physical Society, the American Academy of Arts and Sciences, and the American Association of the Advancement of Science. This is truly one of our very special departments. So, as I said, today we have the pleasure of hearing from Nobel Prize laureate, Dr. Barry Barish. He's the President's Distinguished Endowed Chair in Physics here at Stony Brook. He received his bachelor's degree in physics and his Ph.D. in experimental high-energy physics at Berkeley. He's been on the Stony Brook faculty since last year. He's acknowledged for his exemplary service to science, including groundbreaking research on subatomic particles, his leadership of the laser Interferometer Gravitational-Wave Observatory. I should have just jumped right to LIGO. I hadn't thought of that ahead of time. Led to the first detection of gravitational waves from merging black holes. And what I have found really interesting about this is that it confirms a key part of Einstein's theory of relativity. Actually, a few days ago, I was in China. We're recruiting new undergraduate and graduate students. And one of the things that I talked about was Barry's work, and it was so impactful in that room. And it was just really nice to have a sense of him as a person and to also be able to talk about his work that way. Now, before we move to Barry's talk, as I mentioned, Chang-Ki Zheng, our chair of physics, the SUNY Distinguished Professor as well, Physics and Astronomy and SUNY Distinguished Professor. I want to just say a few words about him. He's received his bachelor in physics from Seoul National University and his PhD in high energy physics from Indiana University. He's been a part of Stony Brook since 1990. His research focuses on the experimental search for proton decays direct evidence for grand unification and the measurements of neutrino particles, in particular CP violating phase. This can ultimately lead to us resolving the matter-antimatter asymmetry mystery of the universe, which will all help us sleep better at night. So without further ado, well, let me just say one other thing. He's really a good chair. And I hope you've had an opportunity to see that. He is such a strong advocate for the faculty, for students, for staff. He balances it in a way thinking about the overall benefits of the university, but it is very clear how passionate he is about physics and astronomy. And you can see in the way that he dedicates himself to the department how much the individuals in the department and the rest of the university benefit. And I have greatly appreciated the opportunity to get to know him. So with that, I will turn it over to Chenki.
Thanks, Carol. I'm a little bit embarrassed now. But let's see. It's my great pleasure to introduce Barish, who I have known for many years as a colleague and also as a friend. And he has done some of the work really, even as a physicist, makes my, skin, the goosebumps. Because thinking about black hole itself is a hugely difficult thing for us to imagine. Imagining two black holes dancing together and then merging and creating this incredible gravitational wave. So, and then detecting that with an incredibly fine instrument and large-scale instrument. So, Barry has received his bachelor's degree and a Ph.D. in UC Berkeley. And then he had, as a postdoc research scientist in Berkeley, as well as Bologna and Caltech. And then he became a faculty in Caltech, and he stayed there until his retirement. And then he became a distinguished professor in UC Riverside. And then last year, he joined us at Stony Brook. So it is a great pleasure to have one of the great minds of our era in our faculty. So his major leadership positions, and he was obviously principal investigator in LIGO when he's the one really, in a way, that greatly influenced making the LIGO detector to work. You will hear about the complexity of that. And then he was a director in LIGO laboratory, and then he also, beside LIGO, he led an international linear collider group. This is a very complex project for some years, and then many other. Also, he was a chair of the APS, president of APS. And so here's some super selected awards and honors: the Nobel Prize in Physics, and then the AAAS member, and also National Academy of Science member. And then one thing not many people know, when he was in college, he was playing tennis. He was contemplating whether to choose tennis or physics. It's a good thing that he chose physics, I think. So that you can see that playing tennis. And then most recently, last year, when he started at Stony Brook, he received the Presidential National Medal of Science. He went to White House to receive these things in the fall, and for his exemplary service to science, including groundbreaking research on subatomic particle. So that first part is important, exemplary service to science. So it wasn't not just recognizing his scientific discoveries and such, but also it recognized his overall contribution to the physics community and to the country. And this photo, I took it, he actually started teaching our graduate students. He started a new course called Frontiers of Physics and Astrophysics. And then when we had him over here, the contract says that he only need to teach one class in a graduate course. But then undergraduate students came in and say, well, Professor Barish, can you do something for us? So he came to me whether we can set up a class for undergraduate students. So he started teaching voluntarily. We had a pilot program last year. And then this year, fall 2024, he will also teach undergraduate students. So I kind of joke to my faculty, all the faculty wants to teach less. Nobel Prize winner comes, he want to teach more. So, all right. So I'm very happy to have him here. And then introducing as a true sea wolf, we took him to a basketball game, men's basketball game. So you can see. So we had a great time, and then he got interviewed in the halftime. So let's go see wolves. And this is something many of you probably watched Jeopardy, right? So he became a subject of a Jeopardy question. And then the question here is that this was a final Jeopardy, right? So the final question which determines the winner is that the Barish, who shared the 2017 prize for detecting gravitational waves, called his award a win for his predecessor. What is the answer? I don't want to hear it, but you should know that, right? So maybe Barry will give that answer. So that's it. So Barry, let's welcome Barry for...
Well, it's good to be back. We've survived the long introductions. I gave a lecture here now a year and a half ago, the first lecture in honor of C.N. Yang, who really was one of the pioneers of the physics department here, but an idol of most of us that grew up in physics in his contributions to understanding, especially the weak interaction, but well beyond that. After that, then I have come back to teach, but I just want to refer back to that lecture because some of you might have been there. I tried to make that a general lecture. I would say this is a general lecture squared. I'm not aiming it at my close colleagues, but to try to give you, as an audience, a sense of the magnitude of the kind of problems that we try to deal with in physics, some of the answers, and the way we think and the way we approach it. So in particular around the field that I'm working in, which is gravitational waves. The picture on the left looks a little complex and artistic at the same time, is a symbolic view of the instrument that I'll talk about called an interferometer, which we use to detect what I'll explain, gravitational waves. And the picture on the top is just the view of what we observed, which is something that most of us have trouble even conceiving of, that is black holes, but two of them that are pairs going around each other with gravity pulling them together, emitting radiation, which makes them lose some energy, and they merge together, and that's what we detected. And that's kind of the punchline that I will get to in a while. So I'm going to start by going back in time. And also what I really want to point at today, which is not so much the physics that we are trying to attack with gravitational waves and even the detection of gravitational waves, but the problem that I think we all can relate to, which is understanding what's out there when we look up, and that is understanding the universe. And we've learned a lot about the universe in recent times. We still know very little, as I'll try to say. And what we have discovered, which has to do with physics, that there are gravitational waves in nature, something predicted by Einstein, represents a new tool to understand the universe. It's so new that we haven't learned that much yet, but we will, I think. So let me reflect back first on what we do know about the universe and how we know it. So basically, of course, from ancient times, people looked up and had all kinds of ideas of what's out there. But the big transformation came in the early 1600s, and it's attributed to Galileo. And Galileo, we all know about Galileo, of course, but one of the things that he did was actually in the early 1600s, where he realized that the telescope had been built, not by him, but by somebody else, the first telescope. It was a period of time when lenses were developed to be pretty good because they were needed for glasses. So lenses were able to be made pretty well. And so he took the idea that people had already done, which is to make a telescope, and he built a 20-power telescope. That means it magnifies 20 times what you see. He had an objective in mind. He decided to look at a common feature of the sky that we have and try to study it with a better view, 20 times bigger. And he pointed the telescope at Jupiter. And when he looked at Jupiter, he saw that there were 4 bright objects near Jupiter. And he assumed, as he would, that those were stars behind Jupiter that were just in the field of view of looking at Jupiter. But he came back a second night and looked, expecting that these stars will have moved because they're way behind Jupiter, either out of the view or somewhere distant. And instead, they were clinging to the planet Jupiter, maybe in a slightly different orientation, but they were near Jupiter. That represented a big discovery. He discovered that there were 4 moons for Jupiter. We now know there's something like 100, but those were the 4 moons of Jupiter that Galileo discovered. That had a large impact because it also represented some tangible proof that Copernicus was right and the Earth was not the center that everything revolved around. Here were little objects that were going around Jupiter itself. So this was the beginning, and the reason I tell the story is it was the beginning of modern astronomy. It was the first time that we used instruments and not just the naked eye to try to understand the mysteries of the universe. And so since that time, the progress has been enormous in what we've learned by using instruments to study the mysteries, if you want, of the universe. And my little picture on the right is the most recent ambitious thrust in that direction. And we've all seen these beautiful pictures that are in the newspapers of the sky viewed by a new instrument, which is was very ambitious to build. Took 20 years. And it's different. And the reason it's different is it looks for the sky in a different frequency band than what we did before. And it's making its own new discoveries in that way. So in my simple-minded physicist view of the way astronomy has developed over 400 years since Galileo came, the biggest change has been in the last century. And that change has been to look at the sky, not just in the visible, where we look with our eyes or with a big telescope like Galileo did, or bigger ones that were made, but to start to look at the sky in different ways where we can view the objects and phenomenon that happen with different probes that tell us different features of what's going on. So here I show the electromagnetic spectrum. That's light, of course, and other frequencies that we're familiar with, from very low frequencies like radio waves to the very highest frequencies like high energy gamma rays, with in between ultraviolet, infrared, and so forth. We know as people living here that having all these different frequencies has all kinds of impacts on our everyday life, which I indicate on the bottom, going from communications and the radio to how we medically can view ourselves best. And this uses the different frequencies. So maybe it's no surprise that in trying to understand the universe using these different frequencies has been so important. But in my mind, the simple-minded way to describe what's happened in the last 100 years 50 years maybe, in the advances in astronomy have been building instruments that look at the phenomena in different frequencies. This is just an example. It's the many faces of a remnant of a supernova. A supernova is what is left when a star burns up all its fuel and dies. And then something has to happen, it collapses and makes a supernova. The supernova is still an object that's there. The star is dead, and you can study it. And in this case, it's looked at in different frequencies, the X-ray, the infrared, the optical itself, and the radio. And you can see that I'm not going to explain it, but the pictures look very different from each other. The different frequencies probe different features like temperature or other features. And that has been basically the main advance, other than more sophisticated tools in each frequency, that has advanced our understanding of the universe through astronomy. In the 21st century, now, we've seen another advance, and we have one example of it so far, but there'll be more. And this was very clever. It was actually to do not just analyzing a phenomenon in different frequencies, but to actually make a combination of pulling together the information alive from different instruments. So I call it combined instruments. This is what's called the Event Horizon Telescope. They built nothing. They just took data from seven infrared telescopes and brought it, they were never made to be used together, and cleverly brought the data together and made it behave, made the data act like it was one interferometer, the size of the Earth, basically. By being a large interferometer, maybe a cruder one, but a large interferometer, they were able then to look at a targeted source. They looked at what is called M87, which is the most visible, most studied black hole that we can see nearest to us in the universe. And the picture on the right, on the upper right, is the picture that managed to be above the fold, as people say, in the New York Times instead of the president during 2020, in the early 2020s, when it was rather unusual to see President Trump not at the top of the newspaper. So we saw science at the top of the newspaper for a change, and that was this beautiful image, which was done, what I'm showing on the left, by taking the data, combining it together, and making a final image from these 7 different instruments. This same group, and that's what happens now, is working to improve this instrument to do something that'll test some of the features that we expect near the surface of a black hole from Einstein's equations. And that is to make, instead of a still picture like we see here, to be able to make what they like to call movies. And that is by adding themselves, which they're proposing to do now, a set of radio telescopes judiciously around the Earth. They cannot make it bigger than the Earth, but they can make it record more quickly, and they can make what they call movies instead of stills like the picture that I have here. If you have a movie of a black hole like this, you can see the surface effects, which are actually predictable by Einstein's equations. So they'll be able to test those. And that's a proposal at the present time, not an actual experiment. But they've gotten the first funding to develop the proposal for the National Science Foundation. So now I'm going to talk about a different way that we're going to look at the sky based on what I've and my colleagues have done, and that is based on gravity instead of based on electromagnetic interactions. And so let me review first just a little bit about what we're talking about. We all know about gravity. We learned it from Newton. And we've probably all seen the equation that I have on the left side, which is basically that if I have 2 masses, they attract each other. That's gravity, us, the apple to the Earth. And the formula goes inversely proportional to the square of how far apart they are, and the product of their masses. And the strength of it is a constant in this formula G, which took another 100 years after Newton to understand or to determine. That was Newton's theory. It is the most successful theory of physics ever. It lasted more than 200 years without it failing to calculate correctly anything that was observed. There was a time in the early 1800s where it was believed there was a violation of Newton's theory, and that was that the detailed orbit of the planet Uranus around the Earth didn't seem to obey the equations exactly. And so that was touted as a possible violation of Newton's equations. But instead, a clever physicist actually reverse engineered the problem and said that if it wasn't obeying Newton's laws, then maybe there was a missing planet. And in fact, by doing that, he discovered that there was a missing planet, Neptune. He didn't tell anybody that, but instead, there's a scientist in Paris. He wrote a letter. He didn't like his astronomer friends in Paris, so he wrote a letter to a colleague in Berlin. He gave 5 days for the letter to get to Berlin, told the colleague where to look up in the sky, and within a degree, he saw the new planet. And of course, he had already given the name Neptune, and so that was a discovery that came from gravity, actually, about the universe. So the first won't be from gravitational waves. But all theories of physics are approximations to nature. We don't have a theory and won't have a theory that describes everything because we don't know everything that we really want to describe necessarily. So all theories, including Newton's, including Einstein's, are approximations. And so having an approximation, when we have a new theory, it doesn't mean the old one was wrong. It means we've gone beyond what it could do and did do. So Newton's theory, which was the most successful theory ever, still remains the most successful theory ever, but it was not able to predict various things that were added in ability to determine by Newton's theory of gravity. The equation on the right in Newton's theory, I just put in to try to give something equivalent to what Newton did, but that's the only equation I'll use in this talk. It's based on geometry instead of a force like Newton's theory. So rather than a force, it's based on effects in space and in time, 4-dimensionally, 3 dimensions of space and 1 in time, as the phenomenon that determines gravity. The only disagreement after more than 200 years, the planet one didn't hold up. The only disagreement with Newton's theory from the time of Newton in the 1600s until Einstein's time was a small discrepancy in the orbit of Mercury. The orbit of Mercury is very elliptical, as I show here. And as it goes around, the positions of all the planets and moons move it, and it comes back to a different place. And you can calculate what the amount that it's going to move is as it rotates around in this daisy pattern. And if you do the calculation using Newton's theory, the amount that it moves is 532 in units that we use arc seconds per century. And the observed movement is 10% larger than that. And that was the only discrepancy that came, that existed when Einstein developed his theory of gravity. Some biographers like to use this as the motivation for Einstein to develop general relativity. I think that's highly unlikely. He had developed what we call the special theory of relativity, the ability to calculate what happens at very high velocities, in 1905, along with solving several other very important problems in physics. And that theory is, of course, based on objects going very fast, relativity, but at constant velocity. And by adding acceleration into the problem instead of just velocity, that's a theory of gravity. That was very difficult. It took him 10 more years. I won't go through any of that history, but by 1915, he had developed his theory of gravity. And it was based on geometry, as I said. It's a four-dimensional problem, so it's very hard to visualize. It's X, Y, and Z, our spatial coordinates, but also time, all intermixed. So the picture I draw here looks like it's a grid, but you might think of it like a trampoline, is that an object that you put on a trampoline, like a bowling ball in the middle of a trampoline, will make a dent like I've shown here. Or in a grid, if I put the Earth or the sun, it makes a distortion, as you see here. Each point on this, it's not going to matter for this lecture, but for thoroughness, each point on this is actually a point in both space and time. So the distortion affects both space and time. We can't quite visualize that in a graph like this. What's shown here is the Earth then going around the sun, and the distortion is what attracts the Earth toward the sun. It's trying to roll down, just like if I had a bowling ball on a trampoline, and I put a marble on, it'll roll toward the bowling ball, but if there's nothing there, it'll just sit. So basically the distortion is created by the massive object. And as I say here, gravity then isn't a force. It acts on space and time, and it's built into the actual structure of space and time itself. And so the other way people look at it is space and time tell masses how to move. So in this case, the Earth around the sun, and the mass itself distorts space-time or tells space-time how to curve itself. So we now have to visualize that we live in a world where space and time are affected by masses. Fortunately for us, that effect is really tiny. So what we think of as a straight line pretty much stays a straight line. But on the scale of the universe, it doesn't necessarily. And so we have various phenomena that basically are affected by this curvature of space and time. So, sorry, my phone. So basically, if we look at what Newton couldn't explain, he told us that the apple was attracted by the Earth, and that's how it falls, but he never told us why. So why did the apple fall, or why when you jump up does the Earth pull you down? Newton didn't explain that. He had a formula, but not an explanation. Einstein does. So the first thing in this new theory is he explains why the apple falls. It's basically shown in this picture here. Anything that's near the Earth will try to roll toward it, or is attracted just by the curvature of space and time itself. The second problem, which is one that Newton actually realized but didn't know the answer to. The first one he didn't say anything about. He wrote this big book called the Principia that described his theory of gravity. He published it in 1687. It didn't say why when you jump up the Earth pulls you down. The second problem with Newton's theory of gravity, he did notice, and he has it in his text, and that is when the apple falls, you as the observer see it immediately. Well, that doesn't matter for the apple falling, you're near it. But if you think if the sun were to disappear right now, we wouldn't know it for 8 minutes because that's how long it takes light to get from the sun to us. And so Newton, using his words, basically realized that his formula had instantaneous action at a distance, and that wasn't physically, there was no mechanism for that to be physically true. And so the action travels in Einstein's theory at the speed of light, the same speed as electromagnetic interactions. So that's enough for Newton. Einstein, in order to have a new theory, isn't just required, as we do in physics, to fix a problem that exists, but to predict something new that basically couldn't be explained otherwise. And he, at the same time, he showed to the Prussian Academy of Sciences in 1915 that he had a new theory that solved the problem of the long orbit being slightly wrong for Mercury around the sun. He basically made a new prediction, and that is that light coming from stars behind the sun, as they graze the sun, would curve. And so he predicted, because of the same phenomena that I just said, so he predicted that if you were to view the sun during a full eclipse at exactly the time when some stars were moving behind it, you'd see the light from those stars bend, basically. And that was proven 3 years later, 4 years later, by Sir Arthur Eddington in a ambitious experiment to the southern hemisphere, where they saw recorded the bending of light from a full eclipse for some stars that went behind the sun. In modern astronomy, this same effect is used as an instrument, and this is also common in science. We learn something, it's a phenomenon itself that's valuable, but then it can help us learn something else. And in this case, we have a phenomenon that's used very commonly now in modern astronomy called gravitational lensing. And that is to notice that an object that may be dark, like the object that I show here, has light that comes around it. And so we can study something about the object. And the most famous one is called the Einstein cross. Somebody's persistent. It's called the Einstein cross, and it's visible almost by the naked eye, often in the southern hemisphere. And so this is a common thing, common phenomenon, and one that we use in astronomy. One more thing before we get to gravitational waves themselves is that something as abstract as a whole new theory of gravity might be important in an actual everyday way. And it turns out that general relativity, very persistent, general relativity has that feature that we use a system every day, most of us, in the little phone that I picked up called GPS to tell us how to get around. And it wouldn't work with the accuracy that we use it without Einstein's general relativity. I'll show you that quickly. Special relativity needs to be used. The system is shown in the picture here. That is, you're walking on your path and trying to follow where you're going, down the road or a path. And in the original system, where 24 satellites, the satellites are high up, and by triangulation, you get signals from some number of them, 4 or 6. And the distance is calculated from all of those. And that's just geometry. But it turns out that because the satellites are going around the Earth fairly quickly, about 14,000 kilometers an hour, they are what we call relativistic, which means you have to make a correction for the fact that they're going so fast. And that correction is actually done in the satellites themselves. It's about 7 microseconds per day. So that the words that we use when we teach relativity is that moving clocks tick more slowly. And so the fact that the clock's moving, you have to make this small correction for that. But there's a second correction that comes from what I'm talking about today, general relativity. And that's due to the fact that the satellites are so high above the Earth. The amount of gravity is only about a quarter of what it is here. And if you do the calculation, which I won't do for you, the clocks actually tick faster because they're so high. And that's a correction that's 45 microseconds per day. And without making that correction, which is 38 microseconds per day, you can quickly calculate the resolution and how long you stay on the road. And if you didn't make the correction, it's just like a couple minutes and you'd go off the road if you didn't make this correction. So we all use this abstract theory of general relativity every day, which tells us that even the most fundamental curiosity-driven research like Einstein's general relativity can have an impact on everyday life. So that's general relativity. The year after Einstein brought out his theory of general relativity, and even before it was validated with the experiment that I showed of looking at an eclipse of the sun and watching the light, recording the light bending around it, he wrote a little paper in 1916 where he conjectured that there were, just like in electromagnetism, there's light connected with electricity and magnetism, that for gravity, there also should be some waves, like electromagnetic waves, there should be gravitational waves. He did this not by a derivation from first principles, but by noticing that if he set up his theory of general relativity in a particular way, the equations that he got looked like what we call the wave equation, which is the equation that we use for waves traveling through space. And so he made the conjecture in 1916 in a little kind of 10-page paper. That paper had some mistakes in it, which he fixed 2 years later when he wrote a second paper. And crucially for me, in the second paper, he talked about how you could create such waves and that they were reliant on the term we use, a quadrupole moment, not a dipole moment like electromagnetic waves. By knowing what I just said, you know what kind of systems will do that. And when we get to a system like two black holes going around each other has a quadrupole moment. So you look for something in nature that'll give that kind of moment. And so he told us how to do that in 1918. He never wrote again about gravitational waves. Actually, quantum physics dominated physics in the next decades. But he came back to the problem in the 1930s, where he, for a short time at least, thought that the theory was wrong in terms of predicting gravitational waves, and wrote a paper that was wrong, but the paper got corrected and published, but it wasn't what he intended to try to do, which is a derivation of gravitational waves out of the general theory of relativity. That wasn't done until after his death. So basically, by the time Einstein died in the early 1950s, there still wasn't certainty that the theory of general relativity gave gravitational waves. That came about a little bit later. Most people dated in a particular meeting in the late 1950s where people were, for the first time, derived it. And even there were discussion of what effects it might have, including an illustration that was given by my colleague Richard Feynman from Caltech. So the problem turned into a challenge, I'd say, for experimental physics in the 1960s. And I won't spend the time on it at this talk, but there was a lot of instrumentation attempts to do this, false discoveries, as we have in physics sometimes, before we got the idea of using a different technique, which I'll talk about just very briefly. This is a picture of what we'll end up detecting in a kind of graphical way. You have to imagine these two things sticking up are two black holes. They're going around each other. As they go around each other, they radiate away, which is being shown. The space between the radiations is the frequency, like we had in light, of the gravitational waves that are being emitted. So we can take, at this point, and calculate for given objects that are doing this, going around each other, what the waves will be like, what their frequency's like, and so forth, using Einstein's theory of general relativity. And that we do as part of measuring and seeing these particles. So what is the effect? Assume there's something like that happening somewhere in space, and then it comes to the Earth. And what I told you is it's going to distort space and time a little bit. So how do we see that? What would the effect be? So here I show, imagine I have a ring of masses. Those little circles, or red circles, are masses. And the radius of the ring is, say, L. And a gravitational wave comes through it. What's it going to do? It's going to change the shape of the circle to an ellipse, distorting space a little ways one way, and then a half a frequency, a half a wavelength later, it'll distort it the other way and it'll be horizontally expanded. So that looks fine. All we have to do is detect that the circle stops being a circle and changes to an ellipse going back and forth. The problem is that the numbers are very small. So if you look at the numbers that I put here, there's something with many, many zeros. The size of the effect is 10 to the minus 21. When we translate that, that's a number. But if I translate that to how much does it really distort this circle, it's about 10 to the minus 21 meters if I have a 1 meter circle. That's a number that's much smaller than even the size of a proton. So it's a tiny, tiny distortion. To measure that is a grand challenge. But it turns out that we have, in general, the ability to do much more accurately a comparison of two sizes that should be the same if they're a little bit different, and rather than an absolute amount. So we have big institutions like the National Institute of Standards, or the big one in Paris that measures how long a meter stick is very accurately, or what a kilogram is. If you're measuring the difference, that's a different problem. And so we have a technique that's quite accurate in general to do that. And that I'll show you very briefly. But what we want to measure is what I show here, this little delta L, which I've exaggerated by making a very big ellipse here. The technique is shown here kind of in a video. We have a laser beam. It goes and hits a mirror. And when it hits the mirror, it sends half the light one direction and half the light perpendicular in the other direction. I show it as a frequency now, a wave that comes. And if I split it in two, when they come back, if I reverse one compared to the other, they'll exactly cancel, as I show here. On the right is the detector, and it doesn't see anything. But if one of the arms becomes slightly longer than the other, which is now superposing on my circle, then they add together and we see a little signal. That's basically the idea. We just have to do it very, very accurately. So the challenge, I'll tell you, the technology, I'll skip. So what we're doing is trying to see, and I'm showing it here maybe once every 2 seconds, a couple times a second. The frequencies we look at aren't that different from that. It's maybe 10 to 100 times a second where we detected black holes. But the picture just looks like the one on the left. And the amount that we have to measure is shown on the right, where I said the number was something like 10 to the minus 21. That translates into being able to measure something, a difference of 10 to the minus 18 meters. That's a very, very small number. As I said, a factor of 1,000 smaller than the size of a proton. To do that, there's nothing that stops us if we can do the interferometer accurately itself, physically, by making it big enough, by making powerful enough lasers with a lot of photons and so forth and so on. What we have to do, the challenge is, and all that was required to succeed is shown in the bottom. There are other problems, of course, in any experiment, but the main ones are shown there, and that is that we have to be able to see the wavelength of the two lights move with respect to each other to 1 part in 10 to the 12th. That's a very, very tiny number. And we have a technical problem, and that is the Earth isn't as stable as we think it is when we're walking around and standing around. It's actually moving all the time at levels that are much, much more than we can tolerate for this experiment. So we have to isolate ourselves from the movement of the Earth itself again, to 1 part in 10 to the 12th. I'm not going to show you those in detail because that's a kind of just technical details, but I'll mention one thing. We built 2 instruments that were capable of making measurements at that level. The one is in the state of Washington, in Hanford, where there's a large Department of Energy laboratory. And the other one is in pine forest, commercial pine forest in Louisiana, Livingston, Louisiana. We originally proposed to build it near Caltech and near MIT. That was the collaboration that we had formed to do this. One in southern Maine and one in the desert at east of Caltech. It went to the government. Luckily, they funded it, but they decided to rotate it for political reasons, to put one in Washington and one in Louisiana. So that's where we live. This is a picture of them. You can tell the one in the left is in high desert. That's Hanford, Washington. The one on the right is in Livingston, Louisiana. They're huge. They're 4 kilometers on a side, and they basically have a lot of instrumentation, a very fancy laser, and it goes down and compares to the accuracy we said, the 2 sides. Just to mention the kinds of challenges that you have, they're all ones you can relate to. We make this simple picture. What limits you? What limits you first is that in going 4 kilometers down the arms, there's atoms in the way. And if the light scatters off an atom and scatters off another one, it finds a path that isn't a straight path to get all the way down to the mirror and come back. And that is an effect that overcomes basically the signal that we might see. Therefore, we have to be at what we call high vacuum. So the system has to be at very, very high vacuum for that reason. The mirrors themselves are basically made out of materials. At room temperature, atoms move around in those materials. They're very fancy mirrors, but atoms move around. And so that creates basically noise, again, that limits us, that the mirror is moving, even if we don't want it to move. That basically is what we call seismic noise. There's thermal noise, which is basically the fact that we're at room temperature and atoms are moving around. That's what I just said. Seismic noise is the shaking of the earth, which we can't totally get rid of. And there's even quantum effects, that is, that we're publishing about now because it's interesting quantum physics at a kind of macroscopic level. And that is that if we run a lot of photons, it puts a pressure on the mirrors and moves them a little bit. So all this is combined together into a very fancy instrument, which I won't describe. And I will describe, just because it's kind of interesting, how you isolate yourself from the Earth to 1 part in 10 to the 12th. We basically, again, didn't have to invent anything new to do this. We already know how to isolate ourselves pretty well from the Earth, from things that are just bumps, by the shock absorber system we have in our cars. A shock absorber in our car doesn't get rid of the fact that you went over a bump, but instead it takes the frequency and makes it with a shock absorber move to low frequency, where instead of, like in a very early car, you went up and down, it just smooths it out so you barely feel that you went over a bump in a modern car. So we made the world's best shock absorbers, made 4 different layers of them, and then hung the mass itself from wires, so it was a pendulum and it wasn't stuck to the ground, and tried to detect gravitational waves. That didn't work because there still was enough shaking of the Earth that it masked any possible signal. So we had to add to that another common thing that we probably have all seen, or the idea, and that is when you go on an airplane and the engine bothers you, the noise of the engine bothers you, you can buy these earphones, like Bose earphones, and you put them on and magically the sound of the engine almost disappears. And the stewardess still can talk to you and ask you if you want coffee, tea, or milk, and that all works perfectly well. The idea is that the earphones are detecting the ambient noise, which is there all the time, of the engine, canceling it. But episodic noise, like a stewardess talking to you, can get through. So that's just what we want. So in our case, the problem's a little bit harder. The shaking of the Earth may be in funny directions that we're left with. So we have to not just detect that it's still shaking, but how it's shaking. So we basically have buried inside of this seismometers that measured where it's shaking and what its direction is, and then we push a little bit back against it and cancel it. That was what we call active isolation. And that got us down to the 10 to the 12th, and then we were able to make this measurement. This is the picture graphically of the detection of gravitational waves. So if you can read it, the left side, the axis says 10 to the minus 21. That's the accuracy we're at. And the scale on the right is time, and it's 0.2 of a second, basically, that the signal was there. And so what you see is some signal getting maybe as large as 10 to the minus 21, getting narrower and higher. The top one is the one in the state of Washington. The middle one is the one in Louisiana. And taking into account just the speed of light between the two and sliding them just slightly, you get the bottom one where one is on top of the other. And that was the picture that was in our discovery paper. I actually prefer this presentation, which is another figure in that paper. So the top is the signals. The middle one is the calculations using Einstein's equations. And the third one down, the little wiggles that go back and forth, is what happens if you subtract the signal from Einstein's equations, or vice versa. And what you get is just a shaking. And that's just the residual noise in the instrument, how good the instrument is. And if there was something else going on, you'd expect to see some sort of pattern there, which we didn't see. So you can take this now and use Einstein's equations to calculate what's going on. And this is the result, and this is probably closest to any numbers that I'll show you. If we do that, we end up determining that one of the there's two objects going around each other. One of them is 36 times the mass of our sun. The second one is 29 times the mass of our sun. And the final mass of the final object, which we can tell by the signal that was there when it got the biggest, was 62 times the mass of our sun. All of us can see that 36 plus 29 is 65, not 62. So there was 65 solar masses of energy originally between the two masses, but the final is only 62, which tells you that 3 solar masses, the amount of our sun in gravity, 3 times the mass of our sun in energy, was radiated away as gravitational waves in 0.2 of a second. That was the brightest object in the universe at that moment. Its distance away, I have it here in megaparsecs, was over 1 billion light years away, 1.2. And that was the very first detection. We've made a bunch of detections since then, but I want to go on to astronomy. So why is this, which is so far totally physics, it's very interesting, of course, got me a nice prize and so forth, but why is it important for astronomy, or beginning to be? So we have to almost go back to 1610 and realize that we've only been doing this for a few years, but we've already begun to learn some astronomy or astrophysics. In order to find, so if you're a sailor or anything else, to be able to find the location very accurately, you need 3, not 2 detectors. And the third one, which was in competition with us, but was slower, we made the detection first, is an Italian-French collaboration near Pisa in Italy. And they were able to make their detector work well enough to put it into a system with ours 2 years after our original detection. And with that, we were able to locate where we were looking in the sky when we saw one of these black holes merge or something in the picture that's down in a small loop. Somehow I can't use this. And all the black holes that we saw never basically were seen by astronomers, but almost as soon as were able to triangulate like this, we saw an event which is shown here. And our signal is this bottom one. And that is, you're looking at time again going across, frequency going up, and the arch is when it merges. And the frequency gets very high and then it merges together. And it comes to a certain place on the very top where it says merger. Within 2 seconds of that, 2 different satellites saw a high energy gamma ray signal. And you can see that as peaks in those graphs. Those are our data. They also were at the same place in the sky, which you see on the right. We were able to point by having 3 detectors and the kind of banana-shaped curves, and the signal that was seen by gamma rays is in the thing called Fermi. And so we saw them together. We had enough confidence then that high energy light or gamma rays were being seen at the same time as signal from gravitational waves. And therefore, we should look and see, or ask astronomers to look and see if they see anything in other frequencies at that place in the sky over the period after that. So we agreed to announce it to astronomers very quickly. We were, of course, poised to do this. Interestingly, the 2 seconds difference between the gravitational wave signal and the high energy gamma ray signal is interesting because first, you expect the gravitational wave signal to come first. It's from these objects going around each other, and you're seeing that signal. The gamma ray signal comes after the object is merged together, and something happens in the object and emits gamma rays. That object's not black holes. In this case, it was what we call neutron stars. So the 2 objects that came together were 2 neutron stars. A neutron star is a nuclear object, very dense, that can be the result of the burning up or death of a star, if it's not so heavy that it makes a black hole. If a neutron star, the neutron star then, as it's made, has nuclear reactions that happen, and that emits radiation, gamma rays, X-rays, and so forth. That takes some time to happen, so you expect it to be a little bit later than the signal from gravitational waves. But in a further analysis, once we understood this was a neutron star, we know what galaxy it came from, how far away it was. It's 150 million light years away. 150 million light years is 1.5 10 to the 15 seconds. These signals are within a couple seconds of each other. So we know just from looking at this, so 1 part in 10 to the 15, that's a very small number, that gravitational waves and light travel at the same speed, as predicted by Einstein, that there is one speed, and that speed was the speed of light and also the speed of gravitational waves. So this requires no detailed analysis, just what I told you. But there was another interesting thing that happened. We knew this was the neutron stars. We alerted the astronomical community. There was the biggest mobilization of astronomical instruments ever. 2,000 different instruments at different frequencies looked at this place in the sky and saw a signal. We recorded the signals. I'm not going to show you in detail. All the way out to the little spots on here are different frequencies going from the highest to eventually radio waves that came days later, something like 15 days later. If we put that all together, you can understand something about what happens in the physics of these two neutron stars coming together. And it solved an interesting problem. And this problem goes back to, I remember it as a graduate student, that basically it's hard to explain, or was hard to explain, how the heavy elements got into the Earth when the Earth was formed. How did we get elements like gold and platinum that we love so much into the Earth when it was formed? The lore is, or the understanding that we have as physicists, is that most of the universe is made out of hydrogen and helium. The place where there's heavier elements is in stars. And stars have a burning cycle, which is basically now well understood to be what we call the fusion reaction. The fusion reaction starts with the very lightest elements, and you burn those up, and you eventually burn up the heavier ones, hydrogen, helium, carbon, oxygen, and so forth. But fusion only works up to, as a fuel, only up to iron. So you can't basically use fusion directly and make elements that are heavier than iron. So how did you make gold and platinum? When I was a student, they basically said there's this funny nuclear process called an R process. It was kind of a game that was causing it to happen. Because physicists always have to explain everything anyways, whether we have a good answer or we don't have a good answer. We now instead have a picture that there's something else that happens in the universe, that there are neutron stars that form pairs, like what we observed, that crash together. And when they crash together, they have reactions that basically can be modeled. There's a reaction, it's called a kilonova, that's in the literature. And it prominently makes things like gold and platinum. And if I just take from the literature and ask for the neutron star merger that we observed, how much gold was made, I show it here. We made 100 Earth masses of gold, or they made, the two neutron stars coming together. Of course, that didn't get into the Earth, but neutron stars colliding earlier did. This is an example of, we don't know yet, because we don't have enough examples to be able to do it. But now the leading explanation, I'd say, for how the heavy elements got into the Earth is neutron star mergers that happened a long time ago. This is, again, a nice illustration of the fact that when we study one thing in physics, it may have an impact in a very different place. We certainly weren't looking to explain how gold got into the Earth. So now, we're making the instrument better and better and taking more and more data. That data basically is seeing some mysteries already, which we're not calling yet discoveries. But for example, we know, and I've discussed black holes, and I've discussed neutron stars. Neutron stars are known to be heavier than our sun, typically 1.4 solar masses, about 1.4 times the mass of our sun, and pretty much that mass, somewhat around it, but near that mass. The second kind of object that I talked about was black holes. But in order to be a black hole, it has to be dense enough and heavy enough so that nothing can get out. That's what a black hole is. In order to be a black hole, it can't be too small and be that. And the best knowledge that we have is that black holes have to be at least maybe 5 times the mass of the sun. So we have a gap between what we think a neutron, and this is our understanding at the present time, what we think a neutron star is, 1.4 times the mass of our sun, and black holes. And we're already seeing examples of events that fall in between. So we don't know yet what. Maybe it's just measuring errors, probably not. But it's an example of us having a new instrument, new ability, and new knowledge that we don't even understand yet. We also have made mergers that are heavier than astrophysicists believed. You could have black holes because of the size of stars. We think the black holes come by the fact that heavy stars, when they die by burning up all their fuel, give a black hole, but we have ones that are already detected to be too heavy to be explained that way. And so basically we're starting our path. This is a very early thing. We basically have less than a decade since the discovery of the first gravitational waves. But progress is pretty fast because there's nothing else that looks like gravitational waves. We don't really have any background. So when we see gravitational waves, they're gravitational waves. We're limited by how sensitive our instrument is. If we can make it more sensitive, we see further out and can see more of them. And this graph is an illustration in just a few years. The change of slope is the rate at which we're detecting gravitational waves. At the present time, we detect some form of a gravitational wave every couple days. So that's starting to be a real science. And with that, we're able to make distributions of what the masses are of them and so forth with the gravitational waves. Just like in astronomy, this has the feature that we can and should and will detect gravitational waves and study the science in different frequency bands. So there's now an approved and funded space mission to make a gravitational wave detector in space. It's called LISA, Laser Interferometer Space Array. It's through the European Space Agency. NASA is also contributing. And it's a triangle that looks like, I won't go into the details, but it looks at a very different frequency range. A third way that gravitational waves are being sought is by looking at something in nature that has very accurate timing, and to look for distortions in the timing due to the passage of a gravitational wave. And that is basically using pulsars. And it's called the pulsar timing array. We have a lot of accurate pulsars in the sky. You look at them relative to each other and look for some passage of a gravitational wave that'll change the relative timing between these very, very accurate clocks. And recently, and say they do different frequency bands, just like I started talking about different frequencies for electromagnetic waves and how that's been so important in the advances in astrophysics. And likewise, we can cover large bands and are beginning to in gravitational waves. The pulsar timing array is just shown here, how it works. And they see what may hold up as a signal and may not, but a correlation where they shouldn't see any sort of shape between any correlations between these different independent clocks. But they do see an indication that is similar to the one that we expect if there were gravitational waves of low frequency. The gravitational waves of low frequency, if they can be detected, are one of the best, maybe the best way to start to understand what happened in the very early universe. Because right now we use electromagnetic waves, but they were absorbed in what we call cosmic microwave background experiments any earlier than 400,000 years after the Big Bang. So if we want to study what happened at earlier times, and we have big puzzles there, then the best probe is either neutrinos or gravitational waves. The most practical one is probably gravitational waves. So with that, I thank you, and you can look forward to many more mysteries of the universe being unraveled, I think. Thank you.
We have time for a few questions.
Well, lately people have been talking about primordial black holes as the origin for dark matter. Is there any way that any of these experiments could shed some light on that?
Yeah. So the question is, let me frame the question a little bit, and then I'll try to answer it. Where do these black holes come from? We don't know. The quickest answer is that they came from the fact that stars, when they die, if they're heavy enough, can make a black hole of the kind of masses we look at. But that's in some doubt because we see these very heavy ones relative to the size of stars. Maybe they came about, these pairs of black holes, by some dynamical mechanism of smaller ones eating up bigger ones and growing. That's a counter one. Or thirdly, maybe them or some smaller ones or somewhat are primordial, that they came early in time. There's many ways indirectly to look at the data as we get more data to try to unravel that. But I think the best is to see the black holes that we see as you go back further and further in time are closer to the Big Bang itself. With the instrument that we have now, we can go to, everything we do right now isn't near early times. But as we improve the instrument, and I think within the next decade, especially if a follow-up instrument is made, it's possible to cover the complete universe, out to the edge of the universe. If we can see black holes, how many there are, what their features are, what the mass distributions are out to the edge of the universe, then we're tracking them back to the earliest times that we can. So in terms of kind of immediate measurements, I think measuring, it's quite plausible, and I think within a decade or so, measuring the black holes back to very early times is the best way to see if there exists before the first stars, for example.
What about the Hubble parameter?
Yeah, the second question is a different one. It's about the expansion of the universe. When we talk about the expansion of the universe, we measure it with a parameter which he just called the Hubble parameter. That's a controversial subject in astronomy today because there's two different ways of determining that parameter, and they disagree with each other. Rather than calling them disagreeing, astronomers call it a tension between the two. Independently and completely in a different way, we can measure the Hubble parameter with gravitational waves, and we have an illustration already of the example that I showed of two neutron stars coming together, using that data to determine the Hubble constant. But we need enough statistics to be able to determine it, and it agreed in general with the size of the Hubble parameter that these experiments got, but not with the accuracy where you could distinguish the two. We need approximately 100 events to be able to do the totally independent measurement, and that should also happen within about a decade.
So this question will show that I'm not a physicist.
Good.
It's more of a history of science question. When I learned college physics, I thought that Einstein was at least in part inspired by the earlier observation of Michelson and Morley, that light's the same, moving at the same velocity in every direction. So I just think it's a beautiful poetic through line that came from interferometry, now measuring gravity waves using basically the same technique.
Yeah, thank you. I agree. Of course, in a different way and with a different objective, but the technique is the same.
But I'm kind of astonished I hadn't heard that mentioned anyway.
Yeah, that's because we don't think as globally as you do.
Yeah, so since the first fabulous discovery of the in 2015 of the two black hole merger, and then that was followed by the neutron star merger just a few years later. So there's been a couple of runs with LIGO since then. This current run has been somewhat disappointing in that there haven't been really many or any neutron star mergers involving neutron stars with it. So although there's been several dozen black hole mergers that were observed. So do you have a feeling for what's going on?
Well, first, it's easier for us to detect black hole mergers. They're heavier and give a bigger signal. So that's true. We do see neutron star mergers, but we have a technical problem, and one reason we're not really concentrating on it very much, and that is that, as I showed, you need a third detector to point in the sky and where something is. And we rely on a detector in Europe to do that, and it's not working. So the run that we're doing now only has the 2 LIGO detectors. So we're not really focusing very much on that. We have the kind of events that I've shown you. We do have neutron-star mergers. We have a neutron-star black hole, several examples of neutron-star black hole mergers. And we have a couple mystery events. But basically the idea of seeing our events in collaboration with, in coincidence with electromagnetic events we can't do during this run because we don't have a 3rd detector. We're hoping the Italian-French detector, which is supposed to turn on this spring when we do, will work better, but I can't judge. It's not our detector.
With all the active cancellation you have to do you ever worry about accidentally, for example, picking up some of the signal and canceling that away, or maybe the active cancellation does some weird things with the transfer function to the noise? Do you ever have to worry about, like, philosophically, the active cancellation systematically tainting your data?
Yeah, let me just say that when we made the first observation of the very first event, we had immediately kind of went into closure ourselves with 2 main questions which we asked ourselves. Now, one was the fact that the very first event that I showed you was observed in September 2015. And basically, it was first observed by one of our postdocs who was in Germany. That tells you something immediately. We're taking our data and we're sending it around the world. So the question immediately came up whether we were somehow being hacked and somebody was inserting a fake event that would fool us. And that, in order to convince ourselves that that wasn't happening, we had to take the data and experiment and basically trace it, which we weren't planning to do, all the way back to the source of the detector itself. The second problem was the form of the one that you said, and that is there some way that we were being fooled by our instrument itself, whether it's active isolation or anything else in the instrument itself? And we, in order to determine that, we have ways to test that by running the instrument in ways that you can't get a real coincidence. You do it by not real. And then we have to do it enough so that we show that the probability of that is incredibly low. And so we set up the instrument to do that. The instrument had just been made to be as sensitive as I showed it. And so we had to actually run it in a mode that tested for the kinds of effects you're talking about for about 1 month before we were able to statistically say it was improbable enough that the instrument itself could have made it an event, whether it was from that or something else.
Thank you very much for the presentation. I wanted to ask you just one small question, which was not really clear for me.
Sure.
Did you understand the physical reason behind the 2 seconds delay of the gamma ray bursts, or is still in ongoing?
Yeah. I waved my hands at it. I can't tell you why it's exactly 2 seconds. But the first thing that's happening is we're measuring these 2 neutron stars going around each other. When they merge, to emit gamma rays, there has to be nuclear reactions that take some time, and the signal then comes out. So I waved my hand saying that time is 2 seconds. I haven't seen somebody do a real calculation that you expect it to be 2 seconds, but you do expect it to be later.
Thanks.
George has promised to ask our last question.
No, it's not really a question. It's a Stony Brook footnote, as I'm sure Barry knows and all of his physics colleagues here, that the issue which we're discussing about the neutron star merger and the production of heavy elements and the observation thereof has one of the heroes of that story is right here, and that's Jim Latimer. Who indeed posed a question, and that's another connection of Stony Brook to this whole story.
So, yes, thank you.
Well, Barry, thank you so much. This has really been all of our pleasure. So let's give a last round of applause.